All right, hey everybody, welcome back. The today we're gonna today's topic is mathematics of decision making, and basically the idea today is last time we learned how to take derivative of a single variable, but now we have multiple variables, and how do we go about doing that? All right, so let's get started. I'm Professor Wu. Well, derivative for a single variable. Last time we kind of learned how to do this, right? So if we only have one variable, x, right, and you take the derivative of this, we have to learn that seven rules that we went over. And that's a seven rule. However, what if x is not a variable? Instead, you're taking derivative with respect to a vector. So this x here is just a variable, right? So that's what we're talking about. But when we make it more complicated, where x is no longer a variable, it's a vector. What does that mean when you are being asked to take the derivative of a function where the input is a vector, right? Well, in that case, the function looks slightly different. In this particular case, x is a vector of three variables, x1, 2, 3, x1, x2, x3, right? So three inputs and then a single output. So this is what that means. And you're being asked to basically find the derivative of this. Well, the result of this is it's actually pretty easy. If you know how to take the derivative of one variable x1, right? You just have to do it three times. Because there are three variables, you just take the derivative first with respect to x1, where x1 is the only variable. That's it. Therefore, x2, x3 are not, right? And then you do that again for x2, where x2 is the only variable, and x1, x2 are considered as constants. And you do that. So if you do it three times, you can imagine the first time you only treat x1, and then you're going to get a function, right? So this is your derivative function with respect only to x1. And you simply do it three times. One, two, three. That's it. That's it. So the result is actually a vector of functions, a vector of functions, right? So it's not just the if your input have three inputs, right? Then you have vector of three functions, right? One, two, three. Right. So let's be clear with the notation. Remember, previously in the last lecture, I told you this is basically asking you. It's like a command. Please take the derivative of this function. Now, when we have a function of single variable, it look like this, right? So the result of taking the derivative is another function, and that's the derivative function. Now, what if x is no longer just one single variable, it is a vector? If this is a vector, then what the result function is called the gradient, right? And the gradient is a vector of functions, as we saw previously. Okay, so this right here is used as the result of taking derivative when your input is a vector, and this is the result of taking the derivative if your input is single variable. Okay, so single input, single output, right here. Single input, single output, multiple input, potentially multiple output. Okay. All right. So, for example, right. So now let's say that you calculated the derivative with respect to x1, x2, x3. So you have three functions. And then what you need to do is you want to find the derivative at that point, right? So if you are dealing with two-dimensional input, at this point, what is the derivative, right? So you will plug x into each function, and each function will basically give you a value, right? It makes sense that you have three numbers because, well, you need to know that at this current point, if you were to increase x, right? If you were to increase, oh, I just realized I should have used a vector of three dimensions, right? Anyways, 1, 2, 1. Anyways, pretend is 1, 2, 1. I just remember we were using a input of three input. Anyways, so it's saying that if you, at the point right now 1, 2, 1, if you were to increase the first one, then it's telling you that your function will go up. If you were to increase the second one, it's telling you the function will go down. If you were to increase the third one, it's telling you that the function will go up again. So basically, the derivative information tells you that at the current point, if you were to increase each dimension, is the function going to go up or down? Okay. So in this previous example, we're trying to take the derivative with this x1, 2, 3, right? And let's say that we want to find the derivative, the gradient function. So we start by taking the derivative only with respect to x1. So that implies x2, x3 are constants, and the derivative of constants are zeros. So it's just this, right? So it's just 2. So derivative 2x1 is equal to 2. Now, then we do it again for x2, right? Here's x2. So now we got the derivative. And then x3 as well, we got the derivative. So now we essentially have 3 functions. With these 3 functions, then we can like plug a point in. So let's say our current point is here, and we can plug x1, x2, x3 in, right, at the current point, and it will give us a derivative. So this is telling us that at this current point, if we were to increase the first dimension, we're going to increase the value of the function. If we were to increase the second one, we're going to decrease the value, and the third one we're going to decrease. So it's telling us exactly which dimension will increase the output of the function and which dimension will decrease the output. And we can kind of visualize this, right? So you can see that here's the x-axis, here's the x-axis. As the x-axis travels, it goes up, it goes down, right? So the function goes up and down. And as the y-axis travels, it goes up and it goes down. So you that's why you need 2 dimension. You need to know if as increase, is it the function going to go up or down? As y increase, is the function going to go up or down? All right. Very quick on finding a derivative when you have summations. Let's say you are trying to find a derivative of the sum, right? Well, a really useful trick for you to realize is that you can simply move the derivative inside. Right? So if you move the derivative inside like this, like right here, yeah, right here. If you move the derivative inside the sum, you can ignore the sum for now. And notice if you take derivative with respect to x, alpha is a constant. So the derivative of this is simply alpha I. And then you could put the sum back in. So you don't have to worry about the sum actually. The sum can be kind of ignored. You take derivative whatever is here and then get the result. Okay, let's do a couple more practices. Over here we have four problems, and let's get a little bit of workout done to see if what we talked about makes sense. Pause the video. Make sure you do this. Okay. The solution for the first question is here. You can pause the video and study it if you need to. The solution for the second one, you can pause the video again. And the solution for the third one, the solution for the fourth one. All right, let's do, so these are not that difficult. Let's do another one, slightly harder. See if you can find a derivative. Well, not the derivative, the gradient function with respect to this function. Okay, pause the video. Here's the solution. Okay. All right, now let's work on more, even harder. Now we have 4 more equations. These 2 equations are actually machine learning, actual machine learning functions that you would need to deal with. These are harder, but they're not that bad. See if you can now pause the video again and give it a try. Okay, here's the solution for the first one. Here's the solution for the second one. Here's the solution for the third one. Here's the solution for the fourth one. Okay. Hopefully, after this much exercise, you are quite comfortable taking derivative of multiple variables. Honestly, we didn't really learn that much. If you remember the 7 rules of like the derivatives from last class, well, this time you just kind of do it a couple more times. That's all. Like you just do a couple more times. If you have 3 variables, you just do it 3 times. So it's not like a huge stretch from the last class. All right, here's another example. See if you can solve this one, right? So currently you have, this is a marketing. You can either spend money on pricing, you can either increase the price or you can put more money into advertising budgets. And you want to maximize R, which is revenue for a company. And basically this is telling you that if you currently are spending this much on each one, then should you be increasing more pricing or should you be doing more advertisement, right? So pause the video, see if you can solve this problem. Over here is the solution. Now, in this particular problem we just saw, basically, we want to know that given our current spending on advertisement and pricing, given our current one, should we increase advertising or increase pricing? Like, what should we do to increase revenue, right? But solving this problem kind of only tells us to increase, but it doesn't tell us how much to increase and to what value we should increase to, right? So you can imagine, let's just look at this. So let's say this is the advertisement that we spend. So if you're currently here, right, and the function says that if you were to increase advertisement, then the revenue is going to go up, right? So that's what we found so far. Well, after you increase, now you're at this point. Well, you can do it again, right? You can do it again. It's going to increase again. And then you can do it again. You can do it again. You can keep doing this until the point where the derivative is approximately 0. Notice at this point, it's neither going up or down. So the gradient of this is perfectly flat. And this is the point of optimal. So how do you go about starting from your this current point all the way to the optimal? Well, you can simply use the gradient stuff, right? You just look at where you are now, increase a little bit, a tiny bit, and then you do it again, increase a tiny bit. And if you keep repeating this, you will identify this point, right? This particular point, which is exactly how much advertisement you need to spend in order to get the optimal return for your investment. Okay, so this obviously you could take a long time, right? So you don't want to do this by hand. You need to actually write the program that would start at some location, find a derivative. If it makes sense for you to increase advertisement, you will increase advertisement. So for your next exercise, your goal is to essentially to write this code. Your goal is to identify this optimum location. Like what is the exact P, like pricing and advertisement you wanna invest on in order for you to maximize. Okay, and the way you do it is to iteratively look at where you are at in the direction you want to go until you reach the point of optimal, which the derivative turns out to be 0. Okay, so this could take a while. So you're going to spend the rest of the class on this. And for those that can finish this, I challenge you to do the very last question. This one is much, much harder. And this leads into what we're going to talk about next lecture. So if you can solve this, then your life for next lecture will be easier. Okay, so pause the video on this one. Really try to understand how to solve this. And then this one as well. And that's it for today.